Okay, in this video, we're going to be comparing the relative importance of the different resonance contributors of the same molecule. So we know that when there are multiple resonance structures for a given molecule, it's a combination of all of these resonance structures that makes up the resonance hybrid that tells us the actual structure of the compound. However, not all of the resonance structures will always contribute equally to the hybrid. Oftentimes, some of them are more important and they contribute more to the hybrid than the other ones. And so the following rules, and we're going to go through them in order of importance, allow us to compare the different resonance forms and decide which ones are the most significant. So the most important rule is that the most significant resonant forms will have the greater number of filled octets. So when I compare the two resonance structures for this molecule, in the one on the left, this carbon does not have a complete octet, and in this one, it does. And so the one on the right, we would expect to be the major contributor, right? And this might be a little bit surprising, right? Normally, we might suspect that having a positive charge on oxygen is not favored because oxygen is so electronegative, but Rule 1 takes precedence, right? And so we want everybody to have a complete octet if we can, because carbon does not have an octet on the left, and they all do on the right. This one is going to be the major contributor, or the more important resonance contributor. Okay, rule number 2 is that resonance contributors tend to be better when there are fewer formal charges, right? So when the total magnitude of the formal charges is 0, right? So of these three resonance contributors, right, first we should probably consider rule 1, right, and look and see, does everybody have a complete octet? And I think they do in the left-hand one and the middle one, but in the right we've got this carbocation where carbon does not have a complete octet. So among these three, based on rule 1, the most important rule, this is the least important resonance contributor. If I compare these two, by rule 1, essentially they're equivalent. Everybody has a complete octet. So then we would go to rule 2, right? In this one, I don't have any formal charges. In this one, I have a positive and a negative formal charge. So this resonance contributor should be more important than this one. And I took this picture from the book. I like the term for this one being a medium contributor rather than the major contributor. So this one should be the most important because everybody has a complete octet. So by rule 1, that's good. And then to break the tie between these two, rule 2, because this doesn't have any formal charges, it should be a more important contributor than the one in the middle. All right, and then if everything is equal through rules 1 and 2, then we would go to rule 3, and this is where we would prefer the negative charge to be on the more electronegative atom. So if I compare these two resonance structures, all the atoms have a complete octet in both. So by rule 1, I can't distinguish them. They both have one negative formal charge. So by rule 2, I can't differentiate them. But from rule 3, in this one, the negative charge is on the more electronegative oxygen. And in this one, the negative charge is on the less electronegative carbon. So this should be a more important resonance contributor than the one on the right. All right, and same thing if I look down here. So I think from rule 1, it looks like everybody has a complete octet. Rule 2, I have one positive formal charge on the left, one positive formal charge on the right. So there's no difference through rule 2. And so for rule 3, on the left, I have a positive charge on the more electronegative oxygen. That's not great, right? But in the right, the positive charge is on the less electronegative nitrogen, so that's better. So the one on the right should be the major contributor. So this is just a summary of the rules, right? And this is an order of importance. So we would check rule 1 first, then rule 2, and then rule 3. So let's take a look at a couple examples. So the first thing we want to do, and I would recommend pause the video and see if you can draw all the different resonance structures for this molecule. And we've left off the lone pairs, so don't forget, right, a negative nitrogen should have 2 bonds. So we've got a bond to the carbon, a bond to the hydrogen, and so it should have 2 lone pairs. And then see if you can come up with all of the different resonance structures. All right, So these are the resonance structures that I came up with. So we have a lone pair allylic to a double bond. So I can move the lone pair down. Then the bonding electrons become a lone pair on this atom, and then I can move. Right now I have this lone pair as allylic to this double bond, and so I can keep moving that lone pair around the ring. And so now when I want to compare these different resonance structures, so I think the one on the far left and the one on the far right are essentially the same, right? The double bond is just in different positions on the benzene. And then I think the middle three are also more or less equivalent. And so the difference between the ones in the middle and the ones on the end, I think if I check rule 1, I don't see anything without a complete octet. So then I go to rule 2. All of the different resonance structures have just one negative formal charge, so they're the same through rule 2. So then I would go to rule 3, and in the 3 in the middle, the negative charge is on carbon, and on the 2 on the outside, the negative charge is on the nitrogen. So because nitrogen is more electronegative than carbon, it would prefer to have the negative charge. So I think the 2 on the outside are our major contributors, and then the 3 in the center are our minor contributors. All right, so here's another example. And so again, I'd recommend, right, first we want to be sure we put in our lone pairs, right? And so I have a nitrogen with no formal charge. So that means that there should be one lone pair on that nitrogen. And so again, I'd pause the video and see if you can draw all of the resonance structures for this molecule. Okay, if you're back, let's compare your resonance structures to mine. So to get these different resonance structures, right, I have a lone pair allylic to a positive charge, so I can move the lone pair down, right? But then that moves the positive charge on the nitrogen, or right, I can move the bonding electrons to here, and that moves the positive charge over here. Right, now when I compare these, when I go to rule 1, we would expect, because we have carbocations in the first and third, right, when we have carbon with a positive formal charge, that means it does not have a complete octet, and so the first and the third, by rule 1, we would expect to be our minor contributors. And then the one in the center, because everyone has a complete octet, we would expect this to be the major contributor. And so because rule 1 can differentiate them, I don't need to go to rules 2 and 3. All right, another type of question that we might see in the book is where they ask us to draw all the significant resonance forms of the compound, and then they want to know whether the benzene ring is electron rich or electron poor. So essentially what we're looking for, if when we draw the different resonance structures, if there are a lot of negative formal charges on that benzene ring, right, a negative formal charge means excess electrons, and so that would mean that the benzene ring is electron rich. If on the other hand, when we draw out all the resonance structures, we see positive formal charges on the benzene ring, then that would indicate that right, positive charges mean a lack of electrons, and so that would indicate that the benzene ring is electron poor. So I might again pause the video, see if you can draw the resonance structure. Remember, this oxygen is going to have 2 lone pairs. All right, so these are the various resonance structures that I was able to come up with. So I have a lone pair allylic to a double bond, so I can move the lone pair down, then the bonding pair becomes a lone pair, right? But in that process, because oxygen essentially went from having its own lone pair to having to share it, it becomes a positive formal charge, right? This guy went from sharing these electrons to getting the lone pair by itself, so it gets a negative formal charge. And then again, I can move those lone pairs around the ring to get these other resonance structures. And so to answer the question, right, is the benzene ring electron rich or electron poor, I can see in these 3 resonance structures, right, we have a negative formal charge on these carbons in the benzene ring, and so I would think that the benzene ring is going to be electron rich for this molecule. And the regions of the benzene ring that would be particularly positive or negative, right, if it has a negative formal charge in one of the resonance structures, right, that's going to be partially negative, right? And then these guys, these sites that don't ever have the negative formal charge, right, they'll probably be, less negative than the ones that have the negative formal charge. Now, the problem doesn't ask this, but if we were asked, which one of these resonance structures was the major contributor, right, I think we would go with the first one, right, because of rule 2, right? This one, nobody has incomplete octets, so rule 1 can't distinguish them. But rule 2, we want the smallest amount of formal charges possible, right? Since there are no formal charges that aren't 0 in the one on the left, this would be our major contributor, and these 3 would be minor contributors.